Last class we talked about the work done by a force acting on a rigid body. A force has two types of effects, one translational effect and second is a rotational effect. Force can produce a torque about the center of mass of the rigid object, which is the cause of a rotation, and force can also accelerate the center of mass, causing the translation of the rigid object. In this way, an actional force is the cause of increasing the translational kinetic energy. It can also increase or change the rotational kinetic energy. In this section, we will discuss the work energy theorem for rigid bodies. If you take a rigid object and consider a force acting on the rigid object from outside, only outside forces can produce torque about the center of mass. The inside forces, the internal forces, cannot produce a torque. Sum of all internal forces is 0, therefore cannot cause any acceleration of the center of mass. Only the external forces are responsible for translation and rotation of the rigid object. The work energy theorem for rigid bodies states that the sum of work done by all external forces, because sum of work done by all internal forces for the rigid object is 0. It is because there is no relative displacement between any two particles, 2 points inside the rigid body along the line of separation. So, internal forces will produce 0 work for the rigid object. So, the net work is done by the external forces only. Then the sum of work done by all external forces acting on the rigid body is numerically equal to the change in kinetic energy of the rigid body. Work done is equal to change in kinetic energy. This is the basic formula of work energy theorem. When you say work for system of particle, the work is divided into two types of work, external work and internal work. Work done by the internal forces plus work done by the external forces is equal to the change in kinetic energy can be subdivided into two parts: kinetic energy translation and kinetic energy rotation. In this case of rigid object, for rigid body, work done by internal forces is 0. Sum of work done by the internal forces is 0. Sum of the internal forces is 0. Sum of torque produced by the internal forces is 0 about the center of mass. All these ideas are very much essential to understand the work energy theorem applied for the rigid object. When we put it 0, we are left behind with one term in the right hand side, left hand side. And right hand side, we have change in kinetic energy, translational, change in kinetic energy, rotational. And this work done by the external forces can be divided into two parts. Number one is work done by the external forces in translating the object, work done by the external object in rotating the object, that I explained in the last class, is equal to change in translational kinetic energy plus change in rotational kinetic energy. So, if you compare left hand side with the right hand side, translation to translation and rotation to rotation. To get to separate equations, work done by the external agent for translation is equal to change in kinetic energy of translation, work done by the external agent in rotating the object is equal to change in kinetic energy of rotation. And I will tell you how to use these two ideas in solving the problems. In last class we proved that work done by the external forces in translation is nothing but F dot dsc. F is the net force acting on the rigid object, and this is the rotational work done is nothing but the work done by all external forces to rotate the object can be written as tau c dot d theta. Tau c is the torque applied or torque produced by all external forces about the center of mass of the rigid object, what we explained in the last class. Integration of this. And I have to demonstrate these two ideas through a simple problems. Let us take an example to explain these two concepts. This is a rolling object. A rolling object. You are applying the force horizontally at the center of mass. When it rolls, friction, which friction? The friction which prevents the relative sliding, that is none other than the static force of friction, acts at the bottom of the rigid body. Let us assume that the frictional force is backward. Under the action of these two forces, along with the other forces, normal reaction and the gravitational force, the body moves. We need to calculate the work done by the applied force, work done by the force of friction in translation and rotation. And secondly, we need to calculate the change in kinetic energy, rotational and translational. And in third case, we need to verify that the net work done by all forces acting on the rigid body, that is the net work done is equal to change in kinetic energy. And we need to verify that work done by all forces in translation is equal to change in translational kinetic energy, and work done by all forces to rotate the object is equal to change in rotational kinetic energy. We need to verify. That's a very basic example I have taken. So for this, we need to draw the free body diagram. I have shown all the forces acting on the rigid object. Let us calculate the first part. Work done by the applied force, work done by the force of friction, work done by the normal reaction, work done by the gravity. In translation, in rotation. These two forces act at this point P, and for pure rolling, the velocity and displacement of this point P is 0. Therefore, n dot dsp or fs dot dsp will be equal to 0. These two are the work done by the normal reaction and work done by the static force of friction. They cannot produce any work because the point at which these two forces are acting doesn't move. So this factor will be 0. Therefore, the work done will be 0. A normal reaction, if you take, it passes through this point, or you can say the gravity, the gravitational force is acting at this point, and this point moves. The gravity and the external force, these two forces are acting at this point. Since the center of mass point moves horizontally, gravity force is acting vertically. The angle between these two vectors, the force and the displacement, is 90 degrees. Therefore, the gravitational force cannot perform any work, and the applied force is acting at this point, and it can perform some work because this point is displacing in this direction. The angle between the displacement and the force is 0 degree. So let us calculate the work done by each force individually. Work done by normal reaction 0, work done by static force of friction 0, work done by gravity also is 0, work done by the external force is equal to F into S. Let us assume that the displacement of the center of mass at which this force is acting is x. Fs cos theta. Theta is the angle between these two vectors, F and S, that is 0 degree. So F into S, but S is equal to x. So the net work done, there are 4 forces acting on the object. 1, 2, 3 and 4. The total work done is equal to F into x. Next, calculate the change in kinetic energy. Let us assume that center mass velocity is v and angular velocity of the body is omega. So change in kinetic energy is equal to kinetic energy final minus kinetic energy initial. Initially, the body was at rest. Therefore, the kinetic energy of the body is 0. Final kinetic energy can be written as half mv square 1 plus k square by r square. If it is, say, cylinder, k square by r square for the cylinder is equal to half, because mk square, the moment of inertia of the cylinder about the center of mass axis, z axis, is equal to m r square by 2. Therefore, k square by r square will be equal to half. You can substitute k square by r square is equal to half. So you are getting 3 by 4 mv square. That is the kinetic energy. Equation number 2. Our work energy theorem states that sum of work done by all forces is equal to change in kinetic energy. So F into x is equal to 3 by 4 mv square. In this way, we can apply the work energy theorem for the rigid body under the special case of rolling, and we have verified this. This portion is over. We have verified, we have used the work energy theorem. Let us now calculate how much work is being done by all the forces in translating the object and rotating the object. Let us see. Work done by the frictional force for translation is equal to frictional force dot displacement of the center of mass. The center of mass moves in this way. Frictional force acts in opposite direction. Therefore, this is minus F into xc. X is x. Work done by gravity in translation, that is 0. Work done by normal reaction for translation is 0. Because gravitational force, normal reaction, both are perpendicular to the displacement of the center of mass, x. Now we have work done by the external force, the applied force F, that we have calculated as plus Fx. So the total work done for translation is equal to Fx minus small fx, that is F minus F into x. So change in kinetic energy of translation is equal to half mv square. Now I apply this concept. Sum of work done by all forces for translating the object is equal to change in translational kinetic energy. This gives us an equation F minus small f into x is equal to half mv square. In this way, we can apply the work energy theorem for translation of this object. Next, how to apply work energy theorem for rotation of the object? Let us calculate the work done by all forces to rotate the object, sum them up and equate this quantity with the rotational kinetic energy change of the rigid body. F minus F into x is equal to half mv square. Let us now calculate the work done by each force to rotate the object. This force normal reaction, this force gravity, they pass through the center of mass, therefore they cannot produce a torque about the center of mass. Therefore, work done by gravity is equal to tau gravity with respect to center of mass dot d theta, integral of that will be 0. Work done by normal reaction, torque produced by the normal reaction dot d theta with respect to center of mass, integral of this will be equal to 0. So these two forces cannot produce any torque. Therefore, they cannot produce any work in rotating the rigid object, the rolling object now. Next, work done by the frictional force. This force of friction will produce a clockwise torque minus Fs into r about the center of mass. And this force, external force, passes through the center of mass, cannot produce a torque, therefore work done will be equal to 0 for rotating the rigid object. So the net work done for rotation is equal to minus F into r. Fs into r, torque tau dot d theta integral of this. This is correct. Tau is equal to minus Fs into r kf dot d theta is rotating in the sense of clockwise manner. So we can write d theta vector as minus d theta kf. Kf dot kf is 1. So minus into minus plus, we can write Fs, take it out of the integral, d theta, 0 to theta. So theta is the angle of rotation. So the static force of friction performs positive work in rotating the object. So this is Fs r into theta. And the work done by all forces in translating the object will be equal to F minus F into x. Change in kinetic energy of rotation is equal to half IC into omega square. Change in kinetic energy of translation will be equal to half mvc square. This will be equal to half IC is equal to half mr square into omega square, and this will be equal to half mv square, the change in kinetic energy of translation of the rigid object. Well, half into half, this is equal to 1 by 4 m r square omega square is change in kinetic energy of rotation. This is the work done by all forces in rotating the object. There is a change in rotational kinetic energy. So you have to just equate these two to get Fs into r into theta will be equal to 1 by 4 m r square omega square. And if you equate these two terms, work done by all forces, sum of work done by all forces in translating the object is numerically equal to change in translational kinetic energy. We are getting this. Already I have noted this equation. So we are separating this equation for translation, for rotation. Work energy theorem for translation, work energy theorem for rotation. We are adding two equations. Well, now we need the relation between x and r theta, the relation between v and r omega. Kinematics of rolling objects. Since the body is rolling, x minus r theta will be equal to 0. Why? If this is valid, dx by dt minus r d theta by dt will be equal to 0. And this is the velocity of center of mass, and this is the angular velocity will be equal to 0. So Vc is equal to V minus r omega is 0. So B is equal to R omega. We know this. We know this. Therefore, x minus r theta will be equal to 0. If we integrate this, we are getting this. V minus r omega is equal to 0. So V is equal to r omega. And reverse way you can prove like this. If you integrate both sides with respect to time, during one period of rotation, 0 to t, we are getting V into t is equal to r omega into t. During one period of rotation, the center of mass moves through a distance x. During one period of rotation, or we can just write, it may not be one period of rotation, during any time also you can just write. The center of mass moves through a distance x and the rigid body rotates through an angle theta. X is equal to r theta. In this you can write. Therefore, the kinematical relation x is equal to r theta. Differentiating both sides with respect to time once, we are getting B is equal to r omega. Using these 4 equations, this work energy theorem, and this is the kinematics. Work energy theorem for plus kinematics. Using these two, we can solve the problems to find the frictional forces, find the frictional force, and the velocity of the center of mass, the omega, all these things you can calculate. Let us try to solve this. Solution of these 4 equations. If you solve these 4 equations, in our own way you can solve. F minus Fs into x is equal to half mv square. Fs into r theta is equal to 1 by 4 m r square omega square. Just divide these 2 equations, equation 1 and equation 2. And by using equation 3, you just cancel these 2, x and r theta. And by using the equation 4, you can cancel v and r omega. will be getting cancelled, half and 1 by 4 will be getting cancelled. You are getting 2 here. So f minus fs by fs is equal to half. So you are getting f minus fs by cross multiplication. So 3fs is equal to 2f. So fs is equal to 2f by 3. That's very fascinating method. By using the work energy theorem and kinematics, we can calculate the value of friction. This is another method. By dynamics also you can calculate the same thing. I may try now, and I will show you that by dynamics you can get the same answer. Once you get this value of static force of friction, other things immediately, one after the other things you can get one by one. Let us try this by using dynamical method, which states that the net force is equal to F minus Fs in positive x direction. That's equal to mass times the acceleration of the center of mass AC. Let us assume that the center of mass has acceleration AC. This is force equation. Then you write torque equation taking the torque of all forces about the center of mass. Equate the torque with IC into alpha, the torque equation. These two forces, F and mg, pass through the center of mass, cannot produce any torque. And the normal reaction passes through the center of mass, cannot produce any torque. The torque is produced by the static force of friction, that is equal to Fs into R. In which sense? In clockwise sense, if you take alpha in clockwise, alpha will be also minus, will get cancelled. And IC is equal to m r square by 2, that is equal to Fs into R, and you are getting Fs is equal to m r alpha by 2, and this is ma. This is equation 1, this is equation 2. This force equation is torque equation, and next is kinematics. Kinematics states that A is equal to R alpha for pure rolling. Using these three equations, you can get this answer. It's not very difficult to show you that Fs will be equal to exactly 2F by 3 by using this method. You can write R alpha is equal to A, so Fs will be equal to Ma by 2, and Fs will be equal to Ma by 2, and here instead of Ma you just write 2Fs. So here F minus Fs is equal to 2Fs, so 3Fs is equal to. So if you substitute Ma is equal to 2Fs, here we can write F minus Fs is equal to 2Fs. So 3Fs is equal to F. So Fs will be equal to F by 3. Answer. But here you are getting Fs is equal to F by 3. So somewhere we have gone wrong, either here or here. So let us recheck this. Here we have half, here we have 1 by 4. If you simplify this term, here we have committed a mistake. Here 4 will be going up, so half into 4, this will be equal to 2. So once you are getting 2, you can just change this term, that's F minus Fs will be equal to twice into Fs. Ultimately you are getting same answer. Absolutely correct. Now in both the procedures, solution of these equations, this method number 1. Method number 1, work energy theorem. Here method number 2, dynamical method. In both the ways, you are getting same answer. In this foregoing problem, we can note couple of more interesting things. If we document the work done by friction for translation and work done by friction in rotation, we can say that these two are different quantities. For translation, it does work, that's equal to minus Fs into x. And for rotation, it does a positive work, that's equal to Fs into R into theta. For translation, or in translating the object, the frictional force does negative work, while in rotating the object, the frictional force does positive work. And if sum of both the work done, you are getting total work done by static force of friction in translating and rotating the object will be equal to minus Fs into x plus Fs r theta, that's equal to Fs r theta minus x. Since it is rolling perfectly, this will vanish. So net work done by static force of friction in the case of pure rolling will be equal to 0 in this case. So we can conclude that the frictional force does negative work in translating this object, and it does equal positive work in rotating the object as a whole. The frictional force doesn't perform any work. Therefore, work done by the static force of friction is 0 for the case of pure rolling. Pure rolling, if the horizontal surface is stationary, is fixed. This is the idea we are getting. So frictional force, even though it is a non-conservative force, it does 0 work. And the work done by gravity is how much? 0. Already we proved. Work done by normal reaction is how much? That is also 0. We proved. Work done by static force of friction 0. Work done by normal reaction 0. Work done by gravity will be 0. And work done by the applied force is equal to F into x. So the net work done will be equal to F into x. And the change in net kinetic energy will be equal to change in translational kinetic energy plus change in rotational kinetic energy will be equal to, this is equal to half mv square. This will be equal to 1 by 4 mv square, because this is half into IC, that is half mr square into omega square. But r into omega is equal to v. Therefore, the rotational kinetic energy change will be equal to half into half, that is 1 by 4 into m r square omega square is equal to v square. So this will be equal to 3 by 4 mv square. So we can equate this two. Again, this is work energy theorem. We can equate the total work done with total change in kinetic energy. We can equate the work done in translation by all forces is equal to change in translational kinetic energy. Also, we can equate the work done by all forces in rotating the system is equal to change in rotational kinetic energy. So this is the way we can use the work energy theorem while we solve the problems of translation and rotation of the rigid bodies. Here one interesting thing I would like to tell you. Even though the frictional force static is a non-conservative force, it does 0 work, but there is another non-conservative force. This does non-zero work, therefore we cannot conserve the total energy of the rigid body.